Julian, thank you very much for such a kind introduction. It's a pleasure to be here and have this opportunity of sharing knowledge I acquired across a journey that was just described, which started from the theory of electricity and magnetism and is now more focusing into how we use that in satellite communication systems. So it's a great pleasure that I have the opportunity to share this with you. Thank you all for being here. I've tried to keep the talk with both generic and specific elements, hoping that someone will find something in it for them. Let's see how I'm going to manage in it. My talk has basically three parts. In the first part, I'm going to be talking about sort of my journey through electromagnetism. So I have to humbly bow to the physicists here and apologize for it, but it's a path that I've taken, and it's been very rewarding. It fits with the environment we're in. We've got James Clerk Maxwell in a hologram just outside this lecture theater, so I'll give my perspective to it. Then, before introducing some top level of where our research fits in the needs of the satellite communication industry, I'll try to give a top level introduction of how these systems operate and what are the key components, so that hopefully the last part of my talk will make some sense to people. So when you get a Greek speaker, you're bound to hear about ancient Greeks. If not, you haven't seen the big fat Greek wedding, long enough. So I'll not break that. I'll start with some etymology. Electricity, electron, comes from the Greek word of electron, which is the ancient Greek word for amber, and is what Thales from Miletus was using to rub and do his experiments and see how you can organize attractive or repulsive forces through electrostatics. That was about 600 years before Christ. He basically had the perspective that once you rub amber, you turn it into a magnet. Something that it turned out to be wrong, because actually it's not what's happening. But then again, it turned out that it turned to be linked, because electricity and magnetism, as it was discovered several years after, they're linked. Another element on the history of electricity and magnetism will be around between 200 BC in China, when the Han Dynasty kingdom, they realized that if you have a magnetic needle floating in water, it will align itself with the magnetic lines of the Earth. Something that before being exploited in navigation was exploited in Feng Shui and aligning your buildings with the Feng Shui. So I'm going to start the talk and the introduction to electricity and magnetism looking at the forces that are produced when you basically rub amber on wool and what happens. And this is something that I hope is reflected in that photo here. It's something that with my daughter Cora we do sometimes. She's not there, she's there. So I've stolen the photo. But basically I think it's something everyone can relate with. You rub a balloon on your wool jumper, and that can then pull your hair because it applies an electric force. And we know that today this happens because you have an exchange of charged particles between your wool jumper and the balloon, and you end up with a balloon that has a net electric charge on it, and therefore it will attract or repel accordingly. It won't move the charge because it's an insulator. Everything is static, so this is the field of electrostatics. And this was, if we move forward 2,000 years from Thales and a bit more, it was 4 years before the French Revolution, where a Frenchman scientist, Coulomb, developed very specialized torsion balances that allowed him to very carefully monitor forces and evaluate forces, and he was actually able to quantify how these forces are described and provide equations on that. Around the same time, there was an Italian scientist known by a French name, Lagrange, and then followed up by a German mathematician scientist, Gauss, who were studying, again, attraction on ellipsoids, and they came up with the law that is depicted here. I'm going to get back to that law. But basically, it says that if we take the lines of force produced by such a charged particle, if we take a closed volume, and then the lines of force that are coming through that volume will be equal to the charge enclosed in it. So if we look at the figure here, there is no net charge in that volume. So as many lines go in, they go out. There is a zero net flow of lines through that volume. In case where we enclose a charge, then we have a net flow of lines, in this case outwards, because it's a positive charge. I'm going to get back to you. At the moment, I find it fascinating always to get a historical perspective into how the human thought around the topic has evolved. So at the moment, I'm just giving that background. We start with 600 BC, 200 BC, just understanding that these forces exist, identifying electrostatic forces about end of 18th century. And about that time, there is a separate set of experiments that take place in Italy. In this case, there was a scientist investigating what happens when you dissect frogs and you put sparks, electric sparks on them, and he realized that the legs of the frogs, they moved. So Galvani, who was performing these experiments, he came up with a conclusion that is actually some innate electricity in the frog. It has something to do with the muscle of the frog. He called that animal electricity. And it was one of his colleagues at the University of Pavia, Volta, who was very excited by the experiment, but not that convinced on the animal electricity concept, who took it from there, developed a very interesting apparatus, what today we would call a battery, so that it allowed him basically to generate current. And today we know that as opposed to the balloon example, a current is a flow of charges. Yeah? So we're talking about charges flowing across a cable. And just for the sake of the story, Volta sort of came with another approach that is nothing to do with the frog itself. It's more something to do with the battery and the cables that connect to it. But together with that, he produced apparatus that was extremely valuable to study this phenomena. So with batteries and capabilities to produce currents, studies and scientists moved further into the study of the electric current. And the legend says that it was during a lecture, actually, that this time first happened, when the Danish physicist Ørsted realized that a magnetic needle would reorientate when he would connect a cable that he had on top of it with a battery. And that was the first sign that a current can interact with magnetism, because we know that the magnetic needle is something magnetic, and suddenly we have a current on it, and that interacts with it. So it was about the time that our university was being founded that another Frenchman, Ampère, took this setup, and then he presumed that if one cable would produce a magnetic force to a magnetic needle, presumably if you put two cables together, there will be magnetism interaction between them. He observed that, he confirmed that, he was able to study it with very good accuracy and obtain actually the equations that produce these forces. And that led to something else that we've done also actually with Cora, which is a very simple experiment on how you can make current go around a nail, and you can lift a needle out of it, because you can produce a magnet out of it. But that's a side story. The other milestone experiment, I'm not claiming that Cora and I have done a milestone experiment, but another milestone experiment, it took place in 1831. It's credited to Michael Faraday, who basically discovered that, in essence, when you have a coil and you can measure the current that would flow in that coil, you have no other source, you have no other battery, and the only thing you do is that you're sticking a magnet into it. And when you do that, he realized that there is a current that is generated around that coil. So again, similar to the experiment of Ampère, there is a link between magnetism and current. In the experiment of Ampère here, we've got current generating magnetism. And here we've got magnetism generating current. And this is where things were. Things were described sort of verbally with some equations, but in fragmented, isolated for a specific experiment until James Clerk Maxwell came about and put all of this knowledge together. He basically, so if we take it historically, 1830s were the experiments around electricity and magnetism, these links. 30 years after, James Clerk Maxwell put together everything that had happened before from Coulomb, Gauss, Ampere, Faraday, and developed the fundamentals of what today we know is a unified theory of electricity and magnetism. So in the approach that Maxwell used, he adopted the term lines of force, and I will stick to that, and I will stick to some other of the thinking vehicles that he adopted, because I think are quite intuitive. So the line of force is basically the line along which a force would be exerted if there was some specimen there to feel it. It is what today in science and engineering we call field. But I think lines of force is nice, is beautiful, is descriptive. So he was studying the lines of force along which forces would be exerted from electricity or from magnetism and from all of these phenomena. And he did that in analogy to waters, to liquids, hydrodynamics. And somehow I find that this is very helpful for me, and I'll try to follow this approach. And I'll start by noting that when we want to describe the movement of water, we have two independent features. They're illustrated in these two figures. You have at the top, you have water that flows uniformly. You are on the top of the bridge with Cora's brother, let's say, who loves sticks, and with Dennis we throw the stick into the river. And the river gently pulls away the stick. So there is some flow, or in the scientific community we use a more Latin term, flux, sometimes. But at the end there's some flow of water that pulls gently the river, drifts the stick away. This is this type of water movement. Another type of water movement would be described by what in the scientific field we call circulation. But I think that picture talks on its own. So it's basically the type of movement that you would have when water spins around. If you throw your stick in, or if you throw your bath ducky in that water there, it won't drift anywhere. It will stay there, but it will start spinning around. So these are the two features of the water movement, if you like: the flow and the circulation. And Maxwell put all his theoretical thinking around describing the flow and the circulation of what he was calling the lines of force, what today we call the electric and magnetic fields. Okay? So those appeared basically in 1861 for the first time in a paper. Just to give you some further of my understanding, and I should say that these are actually slides. Some of these figures, I use them in my lectures. So I've included in that presentation some of my teaching material and some of my research material. Just to understand a little bit about these two distinct features of the water movement, we can do that imaginary experiment together. If we assume that this is a river and the lines are equally spaced, which signifies that the water flow is uniform across, and we throw a paddle wheel in that river, the paddle wheel will drift, but will drift uniformly. It will not spin. Yeah? If we were to drop it in a river that has a faster flow of water at the top than the bottom, it would still drift, because there will still be a drift in the direction of the river, but together it's going to spin, because the top part of the paddle wheel is going to receive more force than the bottom, so it's going to spin. And obviously, if we were to do that here, it was only going to spin. Yeah. So this is just to explain the different natures and the different features of the water flow, if you like, yeah, or the lines of force, the characteristics of the lines of force. So we've already discussed in a previous slide about Gauss law. Effectively, what Gauss law is describing is that if we are to consider a closed volume into that river, unless you have some sort of magic source of water in there, and I call it magic because it's not allowed to bring water in there to pull it out. Yeah? Imagine that you have some sort of spring valve that can generate water and flow water out. Yeah? If you do have that, then you can have some net flow of water outside the balloon that is in that river. If you don't have that, as much water comes in, as much water comes out. Okay? So the first two of the equations of Maxwell about electricity and magnetism is nothing much more than that. They basically say that for the electric field, we can actually do have these magic sources or sink of magnetic field. These are the positive and the negative charges. They have a horrible way to write it because mathematicians are famous for just writing things in a way that only they can understand. But essentially, the first two equations in this month's T-shirt, they describe that. They describe that if we take the total flow of the electric lines of force out of a closed balloon in a river, it will either be zero or it will be equal to the net sum of sources and sinks that we have into that balloon. For magnetic fields, we know that a north and a south pole of a magnet, they always go together. So there is no net source of a magnetic field line. So that flow is always going to be zero. And I think, even though we're not mathematicians, the zero we can all understand. This is the second equation there. Yeah? So the first two of the equations, they're basically these flow equations. They describe the flow of the fields for the electric and the magnetic field. The bottom two equations are the equations that describe the circulation. Yeah? The circulation would relate to that property. So to me, actually, the easiest way I can think of how these equations can be sort of fit, in my mind at least, is around the spinner. I don't know if you've played with a spinner like this. It's a type of spinner that there's a metal pole, and as long as the metal pole is standing there, the spinner stands still. When you move the metal pole in, the spinner starts spinning. So if the metal pole is the flow of the field, let's say the flow of the electric field, if that is static, there will be no circulation of the magnetic field around it. If that is moving, if there is net flow, then there will start being a circulation of the other field. Yeah? So if you have a changing flow of electric field through a loop, you're going to have a circulation of magnetic field around the loop. If you have a change of flow of magnetic field through a loop, you're going to have a circulation of electric field around the loop. Yeah? So the circulations, our friends the mathematicians, they use this to describe circulation, this expression here, that single snake here with this circle. So the circulation of the electric field is the rate of change of the magnetic flux. And the circulation of the magnetic field is the rate of change of the electric flux, yeah? Plus a current. Yeah? Because we know that there are electric currents, there are no magnetic currents. Yeah? But essentially, this is the equations that Maxwell put together, and these equations summarize all we know for electricity and magnetism, classically at least. So they were not presented as such in the first paper. It took a few more years, but all these equations were presented there. So one of the chief achievements of Maxwell was not only to be able to put all of these experiments from all the way from Coulomb to Ampere to Faraday together and come up with these equations and connect everything around these fluxes and circulations, these flows and circulations. But also, most of these terms in these equations had already been observed experimentally. These were the laws of Gauss. They were there for 100 years and more. This is the experiment of Faraday, who was sticking a magnet. This is what you do when you stick a magnet. You change the flow of the magnetic field through the coil. Yeah, there is no field at the beginning. You stick the magnet in. So from zero, you go to something. So you change the flow of the magnetic field. You generate a circulation of the electric field, which means you generate current, and he measured it. So that was experimental. This was what is outside of this circle here. The rest of it was what Ampere has done, what Cora and I have done. You put current around a nail, you connect it to a battery, and you can pick up your pins. So the current, it circulates, you can produce a magnetic field. But this other term here, which is quite analogous to the term above, yeah, which basically says that actually the change of flow of the electric field will produce a magnetic field circulation. That was something that hadn't been observed experimentally. That was something that Maxwell realized it had to be there, just for the theory to be consistent. And one of the chief achievements, and it's not the final one, is that he was able to add this term. Now, why this term is so critical? So I will invite you now to that sort of even more theoretical experiment where we have zero field, and suddenly we have some electric field generated from some reason. We can discuss later how that can happen. So at the beginning, if we take a loop, we had zero flux of the electric field. Suddenly we have an electric field, so we have a flux of the electric field, which means that because of the flux of the electric field, so because of this term, we're going to generate a circulation of the magnetic field around that loop, which means that in front here in the past before we had no magnetic field, now we do have a magnetic field, yeah? So an electric field here generated a magnetic field here, okay? Now if we consider a loop here, yeah, generating a magnetic field here, according to the top equation, we've changed the flux of the magnetic field around this loop. It means we're going to generate electric field circulation around that loop, which means we're going to have an electric field here. So see what we have. We have an electric field here, generating a magnetic field here, generating an electric field here, generating a magnetic field here, and on it goes. So basically, because of that term, you can, and rather than you or me, Maxwell did actually, predicted that electric and magnetic fields and phenomena, not only they are coupled, but they can actually generate a wave. And actually, he was able, because of the values of these coefficients, to estimate the speed of that wave, because these coefficients were known. And then he compared the speed of that wave with the known speed of light at the time, and he saw that it matched. And then he said, light is an electromagnetic wave. It was a major thinking step, starting from things that haven't even been experimented, starting from adding terms in equations that had never been observed, being able to go and say that light is actually an electromagnetic wave, and effectively going against what Newton had said, and all the respect that he was carrying, that actually light is particles. Unfortunately, Maxwell didn't live long enough to experience that he was right. He died shortly after, but experimental scientists followed his work, and they were able to demonstrate, actually. Hertz was one of the first ones that was able to demonstrate that you can set up experimental apparatus, and you can set up this wave, and you can detect that this wave propagates. And this was really the beginning of the radio. This was the beginning of the radio, where from there on, probably science passed it on to entrepreneurship without abandoning engineering. But the man pictured here is Marconi, who started at the age of 20 years old, investigating the experiment of Hertz, investigating how he can generate electric and magnetic waves, developing all the apparatus that will make that more simple. When he was, so I have it here, so when he was in the summer of 1894, 20-year-old, he was actually able to produce a system that could sense an electromagnetic wave generated by a thunderstorm. And make a bell to ring. So he made the first weather prediction alarm system. Then 6 months after that, he demonstrated to his mom that he could make a wireless bell, that you could ring a bell on one side and the bell would ring on the other side without having a cable connection. And then basically within 2 years, he got supported by his family. He got some introductions in Italy. He couldn't get a lot of leverage for his work. He got an introduction to the ambassador of Italy in the UK. He moved to the UK. He found a lot of interest. He got advice actually to patent his work before start disseminating his work. At the age of 21, he was in London, and the rest is really history. He set up a company, Marconi Electronics, for over 100 years. Sadly collapsed with the overinvestment with the dot-com bubble, if you like. But really it's a big success. History that moved a lot, electromagnetic waves. Today we use them across the board. There are different frequencies. Light sits up here. Some of our talk today is going to be around here because these are the waves that we can talk with satellites. Our mobile phones would operate maybe around here. And then FM radio, plenty of applications that are based on these theories and these developments. So it was a massive boom. It was used for the Commonwealth. It was used to transfer signals across the oceans. Radio was a very important development. There was another equally or important development in microwave engineering, in radio technologies. And that came when people realized that, okay, we've got a wave, so if we send a wave, and if there is an obstacle, that wave is going to scatter back. If I receive what is scattered back, then I know that there is an obstacle there. This is the principle of radar. And that was very important during the Second World War. And there was a very intense development of that technology during the Second World War. So the Second World War gave another very quick boost to that radio technology. And together, the Second World War gave a very big boost to the missile technology. So shortly after the war, the combination of the radio technology and the missile technology gave birth to the satellite era. I think the first satellite is Sputnik 1. It was launched by the Soviet Union in 1957. It was about 58 centimeters in diameter. It was probably less than me when the fuel was burned in terms of its mass. And the power that it had is less than half the power you get from a USB key. I think you get 2.5 watts from a USB key. It was operating on 1 watt. It was able to produce, it was at a low Earth orbit, it was able to produce pulses that were received across by radio amateurs and others across the globe. The first commercial satellite then came from the United States in 1965, Intelsat 1, pretty much doubling the mass, 40 times more the power, but still we're talking about less than a power than a conventional bulb would consume. And it was used actually to enable point-to-point communications. So it would act as a transponder. I'm going to talk more about that, to enable links very far apart. The issue there is that because the satellite was small and its power was low, you had to have really 30-meter long antennas, about $10 million in today's finances to set up the terminal. As technology moved and the space segment improved, I've got here in the last photo the photo from AlphaSat, which is Europe's largest satellite platform. You can see some statistics below. We're talking about 6.5 tons. So we're talking about up to 12 kilowatts of power. 6.5 tons at launch, 3.5 tons at dry mass. So it can support 2.5 tons of payload, of useful payload, in addition to the bus. So as this segment developed, together developed a new application of satellites. In addition to doing point-to-point, because the satellite segment was bigger, more powerful, we could shrink down the ground terminal. We could make it affordable to a household, and that was the birth of satellite TV, broadcast TV, which probably still today remains the biggest market for satellites. Okay, so I'll talk you through a few of the components that one would find on a satellite and how these are involved, starting from what we see here, which is, I mean, a satellite. Probably the biggest stuff that you have is the solar panels. And then probably the next one would be the antennas. The antennas would be the transducer that would emit or receive the electromagnetic wave from the Earth to the satellite and back to the Earth. Okay, so I'm going to go back to my liquids to explain a little bit about how I understand antennas. Again, I'm hoping that these pictures talk for themselves. If you basically go back to the liquids, if you basically have a source of a wave, and if that source is localized, yeah, if it's a stone that you drop in the water, it's going to generate a wave that is cylindrically symmetric, a wave that makes wavefronts, as we call them, that are circles and they spread up. Yeah? This is basically, again, attributed to some theories from the 17th century, from a scientist from Lowlands, Huygens, who proposed that every point of a wave is a source of a wave. And at the end, what we observe is the superposition of these local sources of waves. So his explanation of that was that actually what we have is we have every little point here acts as a little source of wave. All of them, they add constructively to make wave fronts that are circular, and they spread up. That's all beautiful and fine. The problem is that if you really want to talk to a satellite that is 30,000 kilometers far, and you use this type of wave generators, your wave spreads. The energy of your wave spreads in circles. And most of it is getting wasted because you want to talk to a satellite that is there, but you're sending your waves everywhere. According to the same theory by Huygens, if you are able actually to put these point sources along a line and you synchronize them carefully, each one of them will still going to generate a circular wavefront, but then all the interaction between them is going to make a planar wavefront. And in this case, the planar wavefront is not going to spread the energy. It's just going to travel along one direction. So if you notice the notation, if you look at the notation in these figures, the wavefronts, there are these circles. In this case, are these lines. They represent what we see here, the circles. Yeah? And the arrows are the rays, are the direction where the energy goes. Yeah? So here the energy goes in all directions. Here the energy goes in one direction. And really, this is much more beneficial for a satellite antenna, because you really want to direct the energy to your target. So this is something that actually going to things that people maybe heuristically have played with. As I said, I come from Greece. There was plenty of sun, a bit like how we are today here. And I remember myself playing with that. You just take a lens, you get the rays coming parallel from the sun, and what you do is that you basically have a piece of glass there that has a special geometry. The wave, because of the property of the glass, goes slower within that glass, which means that the wavefront here at the top goes slower for a shorter length than here, which means that at the other side is accelerated, which means that the planar waveform is converted into a spherical waveform and then to a point. Yeah? So a lens is basically doing that transformation from a point source that produces spherical waves to what we call plane waves, what we call parallel rays, where the energy is directed. Yeah? This is pretty much what the satellite antennas are doing. They are not doing that in transmission as we do with the lens. They do it in reflection. But then again, what you do is very similar. You just play with the geometry of your reflector, things like that. Probably all of us have seen. They follow that geometry such that they can convert a spherical wave into a plane wave, direct the beam. And this is the type of satellite antennas that can go as big as cover the whole valleys and mountains, from as small as what you have outside houses. So with this trick of the antenna, if we take roughly some numbers, when you send a signal from here to AlphaSat, to a geostationary satellite, you lose 10 to the 20 of the power. So 10 with 20 zeros to the power, just because it's so far. Yeah? By doing this trick, you get 10 out of these zeros. So you get 10 to the 10. So you've recovered, half of your orders of magnitude. But there are as many orders of magnitude to recover. And the way you do that is with an amplifier. So the amplifier, what it does is it receives at the input an electromagnetic wave, a signal at a low power, and at the output it produces that wave at a very high power. And roughly in a satellite system, half the orders of magnitude are recovered by the antenna, and the remaining by the amplifiers. So for a spaceborne amplifier, it receives of the order of picowatts, and it transmits of the order of watts. Yeah? This is the scale of magnitude we're talking. Efficiencies for these amplifiers are, there are two main classes. You can get solid-state amplifiers. I'm not going to go into too much detail about that. I think I will need much more time, and you will be very bored. Or vacuum tube amplifiers. This is an example of a vacuum tube amplifier, a traveling wave tube from Thales. Efficiencies range in the order of 30 to 70%, depending on the technology. So if we are to put some numbers on it, if we have a payload that consumes 20 kilowatts of power, we're talking about 4 to 8 kilowatts of heat being dissipated. So this is the equivalent of, depending on your kettle, between 3 to 6 kettles of constantly dissipating heat. And actually, this is one of the big things in getting that heat out, because you're in a very small confined space. And things get worse than that, because actually the amplifier ideally would provide a gain for all signals. I may be getting a bit too specific here, but I think it's quite intuitive to understand that if you put a very high signal at the input, at some point your amplifier cannot provide the same gain. It will start what we call saturating. Yeah? So if you are to input a pure tone, a signal that looks like this is a beautiful sinusoid, it may, for example, crop the ends. And then if you look at this in the frequency domain, what happens is that it generated more frequencies. You start with a pure tone, a single frequency, you end up with more tones, more frequencies. So actually, you cannot operate the amplifier at the very, very maximum of its power because of this effect, which means you have more penalties on efficiencies against what I say, so more dissipation of heat. The other thing that I wanted to highlight, and I put that up, is that because you get these additional tones, these additional frequencies on your waves, you need to suppress them. And in a satellite system, you would suppress them using filters. So another key component in a satellite system is a filter. So let's talk a little bit about frequencies. What does it mean? You basically have, if you do that on a rope, how quickly you move the rope, you get that type of sinusoids that you get up here. Yeah, and if you move it quicker, they come closer together. The frequency goes higher. If you move them slower, they move further apart. Yeah. So the way you would work around to filter these frequencies, because you get more frequencies that you want. For example, due to the amplifiers, you would implement a filter. And if I explain a little bit how the antenna is connected, the antenna has a connection to a tube, because we want to confine the wave into a hollow tube. It keeps reflecting, bouncing in the tube. And in that tube is where we can, for example, implement the filters. And we can do that by okay, these were supposed to have some animations, but not sure they're going to play. Yeah, they do. So if you have a uniform flow of your wave into your hollow tube, and you put a discontinuity there, a part of your wave is going to be reflected, a part of your wave is going to be transmitted. If you put two of them discontinuities, imagine at the first one, something is transmitted, something is reflected. What is reflected comes to the second one, and then is reflected again. Okay? So you have, within that space that you have these two discontinuities, you have two waves that go in opposite directions. If the frequency is appropriate, and the wavelength is appropriate, they're going to add up together, generating a strong field in the cavity, and then a field is going to go through your waveguide. If they don't, you're just going to have everything reflected. So this is a basic principle of how filters would operate, and then if you couple more of these cavities, you can have a more broadband filters, and these are some examples of the filters that we designed and developed here at Heriot-Watt. So now that we've discussed about some key components and we're quite expert with microwave engineering, let's see how a satellite system works. Yeah, so you basically have, let's take the example of satellite TV. So you have users, the users just receive, they just need to receive the TV signal. And you have the operators, you have the likes of Sky TV that they want to broadcast their signal to a number of users. And what they do is that they have big antennas, very, very high quality links up to the satellite. The satellite is going to receive the signal and at a very low power, and then it will retransmit it at a very high power towards the users. In order to avoid interference between what is receiving and what is transmitting, it's going to use a different frequency. So it's going to amplify, so it's going to have an antenna, it's going to amplify, it's going to have filters, it's going to change the frequencies. I'm not going to go too much into that, and then it's going to transmit back the TV. Yeah. If we look a little bit at the market, as I said, 72% of the satellite market is broadcasting, and still is. This is the TV. This is a safe market, but probably not for very long. And the reason for that is the trends and how things are developing. There is a very strong trend for consumers to move from satellite TV to direct to home through terrestrial broadband, through fiber. So already this is observed that the trends for TV distributions are very flat. They're not increasing anymore. And meanwhile, globally, we're experiencing huge growth in internet traffic. I think it's about 22% over the 5 years between 2015 and 2020. The satellite sector captures a small fraction of it, 0.2% or so, but still this is good enough to make a huge growth on the broadband demand. Yeah? And that places a strong challenges for the satellite sector, partly because broadband competition is higher, there are not the same profit margins, but also there are engineering challenges. Some of these engineering challenges are summarized here. If you really want to broadcast a signal, you only have one direction of your link, first of all. You have from the like of your sky to your users. If you're talking about internet, you need your user to be able to talk back to your central feeding point for the satellite. And that means you need to account for a return channel. This is a huge difference. Another difference is that you will need to have a dedicated signal for each and every user. With TV, every user receives the same, and that's fine. They decode and they select. Everyone receives all the channels, and they select the one they want. With internet, everyone, they request for their own signal, so you need to have much more space for signals. So one big trend that the industry is adopting to move in that direction is move from satellite coverage based on language, based on countries, effectively here, to systems that resemble a bit the cellular telephony, reusing the frequency. Yeah? Some of the research that we do tries to address this problem. Other issues is the turnaround, is the cost of the ground segment. I'm realizing I'm running a bit late, so I'll skip through a bit quicker for the rest of the presentation. So with that, I'm going to present some of the work we do here at Heriot-Watt. We try to basically perform research in microwave and antenna engineering that is going to address the needs of this satellite sector and the transition to internet applications, all the way from the co-design of the antenna with the coverage and the optimization of how you do that, to setting emulate satellite systems on the test bench and measuring the throughput of them, all the way down to components, amplifiers, filters, and antennas. Some of highlights of the projects follow in the next few slides. As I said, I'm going to run through them. One of the things that we participate is the QV band experiment from the European Space Agency. As I said, there is a big throughput link between the user of the satellite, or let's say the operator of the satellite, the Sky TV, or your internet provider, and then there is a different link, a different frequency for the user. At the moment, these two bands are the same, but critically, only the second part generates income, because it's only the users that pay. So one of the things that the industry is looking to do is move the link from the gateway, from the main link, to the satellite, to other bands, higher bands, and that potentially can allow them to have less of these gateways and also to generate more income from the frequency. So the European Space Agency is coordinating a campaign at new and higher frequencies, and I think we are working with colleagues at NASA, and I'm very pleased that they're here today to record that signal here in Heriot-Watt. We have one of the 3 terminals in the UK for that signal, and work on the statistics of those. We also work with the National Space Research Agency, RAL Space, who are actually the owners of the other 2 terminals, in activities to try to coordinate that system globally. And the coordination globally really is highlighted in this project. That's a European Union project where we participate, where because these frequencies, they suffer a lot from attenuation, you really need to have a lot of redundancy. So if you have this gateway at new higher frequencies, because that gateway may no longer be available if you have a rain, you need to be able to reroute the traffic through another gateway. So that European project is actually operating on the same experimental payload on AlphaSat to perform this type of experiments. I was going to talk about chicken and ovens, but I think I'm running out of time. I'm a microwave engineer, so I have to have a microwave oven somewhere. The reason I was going to do it is not so much to explain that you need a rotating dish to avoid the nulls in a standing wave of a microwave oven, but more to draw your attention at the grid that you have here in front, which is some sort of frequency selective grid. It allows light to go through, so you can see if you've burned your chicken, but it doesn't allow the microwave radiation to cook you together with your chicken. And this frequency selectivity is something we are designing, and is something we're applying in the use of antennas that can produce this type of coverage without dedicating an infinite number of antennas, reflector antennas, on board the satellite. That area is something that we're also coordinating a European-wide doctorate school. This is in very close partnership with Thales Alenia Space in France, and is basically looking at the needs of a number of emerging missions, and how you can bring technologies from additive manufacturing, from deployment of structures, from analog digital co-design, in order to provide the solutions to these problems. Another problem we've dealt with is how you can improve the power handling. It has a very cool name, multipactor, yeah? So it's basically how you can improve the power handling of your spaceborne components. There are some phenomena around the buildup of electron clouds, and yeah, it's basically how you can insulate your filters so they can take more power. We've also worked on the ground segment. We've worked on, we coordinated a European project called Dorada, where basically we've developed technologies for amplifiers for the ground segment at low cost, characterize these amplifiers for nonlinearities, deal with that, set up test beds, end-to-end links, and also perform some research on a very important element of satellite communications, which is the flat panel antenna. That will be my penultimate slide. So the flat panel antenna, it basically means that if you really want to have a big market, and if you want to have antennas on airplanes, on cars, on trains, you cannot have that. You need to have something which is small for aerodynamics reasons, for all sorts of reasons. This is a project that we started in the framework of Dorada. We followed up with space engineering through funding from ESA, and currently we're working with the Scottish enterprise to commercialize that research. So with that, I'm just going to briefly summarize challenges and future trends. It's all about cost. It's all about the competition. It's not so much about the performance. The performance is there. The point is how you can get the market and penetrate the market. There are roughly two big approaches in the satellite sector. One says, let's make the satellites even bigger, the geo satellites, more power, more capacity, and therefore the cost per bit drops. Flexibility is very important because there's no point to have a lot of bandwidth over a country where there is, in 10 years, war. There is no market. So flexibility is also a big issue on that. Another big approach is around, okay, let's make satellites super cheap and let's have loads of them. And this is really pushed aggressively by several investors primarily in the US on lower Earth orbit and medium Earth orbit constellations. And really the technologies around that are what are being looked. So with that, I would like to first acknowledge the team, and it's only a small part of the team shown here. Thank everyone. Thank colleagues and mentors throughout that path. Partners, collaborators, obviously our funders, and of course, thank you all for listening to this talk. I hope everyone gained something. Thank you.